So, what's up, guys? So, this video is inspired by Matt Parker's 4 has 4 letters video on his YouTube channel, Stand Up Maths, on the 10th of September 2016. I'll put the video link down in the description, so do check it out after this video, right? So, in his video, he assigned homework for the viewers, and today I want to attempt to answer them one by one and put attention to the third question. Right, but first here's what the video is about. He explained and described a function mapping out numbers to its number of letters and continue the cycle, right? So for example, 7 has 5 letters, 5 has 4 letters, and 4 has 4 letters. Then 4 loops itself back. So this is a 3-numbered chain, excluding the loop. And this 4 is a 1-number loop. Okay. Later on, he conjectured that all linguistic system has this same feature, which is there is a threshold number, which is called its k, where any number above that number will have the number of letters less than the number itself. So in English, in the base 10 level or decimal level, the k is 4. So we have 1, 2, 3, 4, 5, 6, 7, 8, and so on. So I just write down 4, 5, 6, 7, 8. So this is our k in English. So 1 has 3 letters, 2 has 3 letters, 3 has 5 letters, 4 has 4 letters, 5 has 4 letters, 6 has 3, 7 has 5, 8 has 5. So you can see here, and any numbers above 4 will have its number of letters less than the value of the number itself. And that's it. So the first question to his homework is, can you find a number such that it produces a chain longer than 7? Because the video claims to be found that the longest chain is 7. So he asked us to find maybe 8-number chain or a 9-number chain. So this question has been actually done by someone before it was published. Right, on the 4th of July 2013, Bronnonier, who is in Germany, had discovered this long number, right? So it's 1 nonillion, 103 octillion, 323 septillion, 373 sextillion, 373 quintillion, 373 quadrillion, 373 trillion, 373 billion, 373 million, 373,373. Now this long number has 323 letters, and from there you can work on, right? 323 has 23 letters, 23 has 11 letters, 11 has 6 letters, 6 has 3 letters, 3 has 5 letters, and 5 has 4 letters, producing an 8-number chain. So that's basically the first question. There is a link to the to an OEIS page showing this sequence. I'll put the link down in the description, and also a page to show you which smallest numbers will give a certain number of letters. So like just now, that huge chunk of numbers is the smallest numbers to give 323 letters in total, right? So moving on to the second question, which is about loop. So the video gave us an example in French, which is 5, 5, my pronunciation, has 4 letters, 4 quadrat, has 6 letters, 6, has 3 letters, 3 choice, has 5 letters, forming a 4-number loop. Okay, so English, apparently there's no loop as mentioned in the video that Stand Up Maths has posted, right? So Now, I'm Malaysian, so I can speak for three languages mainly, which is English, Malay, and Mandarin. English has been covered, so I'll cover Malay and Mandarin basically. Right, so in Malay,
Empat, 4, has 5 letters, and 5 lima has 4 letters. In Chinese, interestingly, 4, 4 has 5 strokes, and 5 wu has 4 strokes. So in Mandarin, we don't have letters, so we use strokes because a different word has different number of strokes, right? So Malay and Chinese, there are 2 number loop.
but the case doesn't stop here. The word for numbers we use today in Mandarin are pretty much simplified. Back in ancient China, the word for each numbers is made complicated to prevent changes in numbers when it comes to accounting issues. Guys, so these are numbers. Today we call these numbers as capitalized, as in capital letters in English. So these are the simplified numbers, and these are the capitalized numbers. And we seldom use them already because it's too troublesome to write and memorize. Okay, so if we use this system, I found two loops which are two numbered and four numbered respectively.
Okay, so the first loop is 7 and 9. So 7 chi has 9 stroke in this system, and 9 jiu has 7 stroke. So they loop each other. And the second one is rather large, but it's 4 numbered. So the first one started off with 25. So 25 has a total number of 24 strokes. So you can see 9 plus 9 plus 6 is 24. Then we map this to 24. So 9 plus 9 plus 13 is 31. Okay, so 24 has 31 stroke, 24 has 31 stroke. So we map this to 31. And 31, as you can see, 31, you add them up, 8 plus 9 plus 12 will give you 29 strokes. So we map this to there. And 29, if you add them out, the total number of strokes is 25. So this will give you a 4 numbered loop as well. Okay, and that covers our second question involving loop.
So I can't find anything above 4. So the maximum I can find is the 4 numbered loop as mentioned earlier. Okay, moving on to the third question. The third question of the homework is asked to find a k larger than the video suggested.
The video suggested is 18. The binary is 10010. So 1 has 3 letters, 0 has 4, and if you add them all up, you'll get 18. And any number above 18 will give the total numbers of the letters less than the value of the numbers. So k is 18 in an English binary form.
I did some research and do found some k greater than 18 in different systems. So let's go through the Malay and Mandarin again in base 10. So in all three English, Malay, and Mandarin in base 10, k is essentially 4. Anything larger than 4 has its number of letters or number of strokes less than the number itself. However, in the capital numbers in Mandarin, k shoots up to 28.
So here, so 28 has 28 strokes, and any number above 28 will have the number of strokes less than the value of number itself. Okay.
So let's go back to the binary world. In English, we have k equals 18. So 10010. Okay, now before finding k in binary in other languages, I want to mention a method I use such that it wouldn't be a proof by exhaustion of finding a k by exhaustion, which is running numbers one by one. So
Since binary composed of two digits 1 and 0, okay, you can find that 1 has 3 letters and 0 has 4 letters. So basically any binary, this one is in English, right? I start off in English and work my way up to Malay and Mandarin because the method is essentially the same. So any number in binary will have 3x plus 4y.
total number of letters.
Okay, and here I plotted the graph. Okay, the x-axis is the number in the decimal value, and the y-axis is the sum of the total number of the binary form. So we have, let's say, we have 63 here. 63 is 11111 in binary base 2, and that gives us a total number of 18. So you draw here and go here, you get 18, right? So this is the graph, and interestingly you can see there's a lower boundary and an upper boundary. Lower boundary is in red, upper is in blue. Okay, so you can see that there's a lower boundary because for a minimum n you need y to be 0, and x could be any number. So that gives you a lower bound. So this case of number is essentially 2n minus 1. Now for the maximum of n, you need a maximum of 0, you need a maximum of y.
But you can't start a 0 without a 1 at the front, so you need at least one x.
So x equals 1 and y could be any, such that you get this upper bound, right? So eventually this maximum is 2 to the power of m, right? Because it gives you 1 followed by zeros. That gives you this maximum line.
From here we can plot
Another graph, you can, where the x-axis is 2 to the power of n for each cm. So 1 cm is to 2 to the power n, n is 0, 1, 2, 3 and so on. So we have 1, 2, 4, 8, 16, 32, 64, 128, 256 here. And for the y-axis is 1 cm to 5 letters, right? So as in this graph, 1 cm is 5 letters. You could expand and so on to get the same graph. Okay, so we can see here 1 has 3 letters in total, 2 has 7 letters in total because 2 is 1, 0, 7 letters in total. 4 has 11 letters in total because it's 1, 0, 0, 3 plus 4 plus 4 is 11, and so on. You get this nice linear straight line, which is y equals 4x plus 3. 3 is the y-intercept, or the number of letters of the 1/2 in the language, right? In this case English, and the gradient is the number of letters, the 0/2, so in English is 4. Okay, so you can see here 2 has 7 letters, which is more than 2. 4 has 11 letters, more than 4. 8 has 15 letters, more than 8. 16 has 19 letters, more than 16. 32 has 23 letters, less than 32. So we know that k is between 16 and 32 because if the upper bound does not have the number of letters more than the number itself, then the rest of the numbers below them will not have that. Yeah. apparently it's something like that. So we know k is between 16 and 32. We look back to this graph, we plot. You can see that 18 is between 16 and 32, which is correct because the video suggests k to be 18 in binary English. Now, using similar method, we can find that in Malay, 1 is satu, so the y-intercept is 4, and 0 is kosong, so the gradient is 7. So if you plot this graph, you can find that k is between 32 and 64 because 32 has 39 letters more than the value of 32. 64 has 46. 64 has 46 letters in total, less than 64 itself. So k is between them. And if you run the numbers one by one, you get 36. Okay, in Chinese simplified, it has 1 stroke and Ling has 13 stroke. So you plot this y equals 13x plus 1 graph, and you can get k is between 64 and 128 if you correspond it back. So after writing numbers, I found out k to be 66. And finally, the capitalized number, k is 88. Right, you can see in the graph here. Because 1 has 12 strokes, so the y-intercept is 12 and the gradient is 13. Ling is also has 13, is the same as the simplified form. So the gradient is 13. So you get this k between 64 and 128. And essentially k is 88. So you can get that far. So now k is 88.
Can we go higher? I think we can. What about the other bases? Can we find a k in other bases like base 3 and base 4 that is higher than 88? Again, I'm only talking about the language I know, Mandarin, Malay, and English. Now, for a higher k, I'm thinking of the following requirements, though I don't know if it's true or not. But the number of letters or number of strokes have to be as large as possible. So each unit of word will take up as many letters or as many strokes as possible. Also, the base should be as small as possible because larger the base, the greater the value each unit takes up, the shorter the number, right? So the criteria do not fit in the language I know. So the largest k I found is 88. Do comment down below if you discover a k greater than 88. And that's it. Thank you and peace out.